Giovanni, for your kind introduction, and let me give the chance to thank all the other organizers, Francesca and Massi, for inviting me today to deliver this talk. It's a very great pleasure to this virtual workshop on seismic and metamaterials. Well, the topic of my presentation is on innovative isolation systems that exploit the unique properties of inerter-based vibration absorbers. I would like to start my presentation by an overview of a traditional base isolation system. So there are many typologies of isolators in the world. The most commonly used ones are rubber bearings, or bearings with a central cylinder made of lead, so-called lead rubber bearing isolators, or isolators mechanism of friction, so friction-based isolators, like friction pendulum systems, in different variants, like single, double, or even triple curvature of the devices, or flat slice in combination with other dampers. All these technologies share a common underlying philosophy, that is to disconnect the motion of the substructure from the ground shaking by interposing a flexible layer in between the substructure and the foundation. And besides these traditional isolation technologies, there are also some combined isolation systems. I report here some examples taken from the web. For example, in the Great Mosque of Algiers, a kind of friction-based isolation system that is combined with the dampers, hydraulic dampers, in order to achieve a so-called adaptive hysteretic behavior. Or, for example, in many bridges, where we have a combination of rubber isolators with other kind of dampers like transverse and longitudinal dampers. So one of these concepts was proposed quite recently in a publication in Engineering Structures, is to combine friction-based isolation with the shape memory alloys gap dampers. So why this combined isolation system? Because we can accomplish a very interesting hysteretic behavior, which is shown in the lower right part of this slide. I mean, an adaptive hysteretic behavior that is different depending on the intensity level of the earthquake. In the low range of displacement, I mean, for earthquakes having a low return period, like visibility earthquakes, the behavior is similar to a low friction isolator. But as soon as the displacement exceeds a certain threshold called the gap displacement, there is an additional energy dissipation and stiffening effect provided by these shape memory alloy gap dampers. This combined isolation system was studied numerically. We proposed an optimal design procedure, and we also numerically tested its validity against experimental results in shake table tests. In particular, we considered two kinds of earthquake ground motions, so-called low to moderate earthquake intensities and strong earthquakes. So let's start before with the strong earthquakes. For strong earthquakes, I mean, maximum credible earthquakes that can happen just one time in all the service life of a structure, we want to avoid the damage of the isolation system. So we want to limit the displacement of the isolation system. And if we have a look at the graph here, we can see that the displacement demand is considerably reduced in comparison with the low friction isolation system, and is even lower than high friction isolation system. So it's very good, the behavior for strong earthquake. So now let's have a look at the response for lower intensity earthquakes. If we have a look at the hysteretic loops, we can see that the behavior is exactly the same as the low friction system. So because the shape memory alloys, the gap dampers are not engaged in the hysteretic response, so they don't work completely. And in terms of absolute acceleration, we also observed that there is a similarity of the response to the low friction system. Absolute acceleration are very important, especially for critical buildings like hospitals, because of the protection of no structural component that are particularly critical to absolute acceleration. So we can combine the advantages of low friction and high friction isolation with this combined system. Another kind of combined isolation system is based on the combination with the tuned mass damper. So this concept is well known. It's based on the transfer of kinetic energy from a primary system to a secondary mass, a secondary system. So the most emblematic example is the installation of a large mass of around 700 tons in the Taipei Tower in Taiwan, and this mass moves out of phase with respect to the movement of the high-rise building. So this concept was exploited in our recent work in order to propose a combined isolation system with the tuned mass damper. We applied this technology for the earthquake protection of a university center located in Palermo in South Italy. In particular, we developed a project by planning a traditional set of rubber bearings placed around the perimeter of this building in order to increase the torsional resistance of the building. And besides this traditional isolation system made of rubber bearing, we designed a large mass TMD located at the basement of the building. So this large mass is connected to the isolation floor through a set of additional bearings, in this case lead core rubber bearings, and was tuned in order to mitigate the displacement demand of the isolation system and to improve the seismic performance of the substructure. If we have a look at the modal analysis of this structure, it is quite peculiar because we have the first three modes of vibration of the building involve the motion of the large mass of this TMD at basement, while the substructure, including the base isolation system, is almost at rest, so it is not moving at all. And we have the classical three modes of vibration: translation and torsional modes of vibration. Instead, the fourth, fifth, and sixth modes of vibration involve the combined motion of TMD base isolation system out of phase with respect to each other. We can see that when the base isolation system moves from the right to the left, the TMD moves in the opposite direction. The same can be said for the torsional motion. The question is, how can we design these connection layers? So the isolator that connects the large mass to the isolation floor. So this was done by developing a simplified model, a 3 degree of freedom model, including the substructure, which is a 1 degree of freedom, the base isolation floor, and the TMD, which is the 3rd degree of freedom. And we proposed a stochastic-based optimal design procedure in order to tune the stiffness and damping properties of these auxiliary isolators that connect the large mass to the isolation floor. I don't have enough time to explain all the details of this optimal design procedure, but I just want to focus on the results. I mean, some sketch of the results in terms of seismic performance. Let's start with the interstory drift, which is a very important response indicator for a building because it is closely related to the damage of a building. If we have a look at the interstory drift of the second level of the building, we can see that the response is dramatically reduced in comparison to the fixed-based building, which is expected even in the classical base isolation building. But if we have a look on the right, we can see that the addition or the installation of the TMD reduces further the response in comparison with the classical base isolation building. And also in terms of displacement demand, there are very high displacement reduction for the isolators. So we obtain a very effective isolation system. Well, these results are somehow preparatory for the development of an innovative isolation system that is combined with inertial-based vibration absorbers. What is the inertia? The inertia is a relatively new concept that was developed at the beginning of this century by Professor Malcolm Smith at the University of Cambridge. It is a two-terminal device whose resisting force is proportional to the relative acceleration between its two terminals. So it somehow completes the first current analogy between the electrical and mechanical networks. It is accompanied by other well-known devices, which are the spring and the damper that produce forces proportional to the relative displacement and relative velocity, respectively. So the inertia is another device whose force is proportional to the relative acceleration. And the constant of proportionality, which is called B in this slide, is termed inertance, and it has the dimension of a mass. It is measured in kilos. So the peculiar characteristic of this device is that it produces a very large mass amplification. I mean, and this thanks to a conversion of the translational motion to a rotational inertia. So there are many technologies to realize the inertia, like rack and pinion mechanism or both screw devices. For example, with a device of just 2 kilos, an inertance of apparent mass of around 350 kilos can be obtained. So we have a mass amplification of around 200 times. So this device was largely used in the automotive field to realize effective suspension systems. For example, the McLaren, driven by Kimi Raikkonen in 2005, mounted this kind of suspension that is called the J-damper, which is nothing but an inertia in parallel in series with a spring and dashboard. So our idea is to exploit the inertia for structural vibration control. In particular, we want to realize a combined isolation system with tuned mass damper inertia. So this new lightweight and more effective vibration absorber combines the classical TMD with an inertia that is grounded, I mean attached to the ground, and due to its inherent mass amplification effects can increase the performance of the tuned mass damper, because we know the larger the mass of the TMD, the more effective the behavior of the TMD is. And so this TMD high was proposed in combination with the base isolation system. What are the motivation? What are the reasons for this combined isolation system? So there are many answers. In particular, with this system, we can reduce the displacement of the isolators. So we can adopt smaller size isolators, which implies a lower cost for the overall isolation system. And this also has important implication in terms of reduction of the flexibility of the connection for utilities. I think about elevators, gas ducts, electrical conduits, or pipelines, and everything that should accommodate the displacement of the isolation system. We also reduce the risk of mutual collisions between adjacent isolated buildings, which is a critical problem in densely populated areas like, for example, in China. It also reduces the vulnerability to particular class of ground motion, in particular near fault and long period ground motion, that can trigger resonance phenomena and amplify the displacement of the isolation system. We demonstrated in 2 publications publications published in earthquake engineering and structural dynamics that this TMB high is more robust than the classical TMB. I mean, it's less sensitive to variations of the system parameters, so of tuning or detuning condition, which are a critical problem, a critical issue of vibration absorber. And this may occur for different reasons. For example, the reduction of the hysteretic properties like effective stiffness or reduction of friction coefficient due to the cycling effects occurring in the response to a given earthquake. But the most interesting application of this concept of the inertia is the fluid inertia. I mean, the fluid realization of the device. If we have a look at this device, it has many similarities with the classical fluid viscous dampers. So the most commonly used dampers in the world, which implies a transfer of fluid, of a silicon fluid from one chamber to another to dissipate energy. So in this case, we have a piston cylinder technology, so similar to the fluid viscous dampers, but instead of an orifice to convey the fluid from one chamber to another, there is an external helical channel that conveys the fluid from this side to this side. So we have the linear motion of the piston generates a rotational inertia of this fluid mass. This device was patented quite recently, almost 10 years ago, and its working principle based on simple hydraulic mathematics. But there are some advantages of this device in comparison with the classical mechanical inertia. In particular, it employs a technology that is widely used in earthquake engineering, so the piston cylinder technology, and it can also reduce some undesirable phenomena, friction-related phenomena that occur in the mechanical gears. We performed some tests in collaboration with a group of the University of Sheffield on a small-scale prototype of this fluid inertia, of this fluid device, and we proposed a simplified model of an inertia in parallel with the nonlinear dashpot element with a power law coefficient of 1.75 to capture the hysteretic behavior of this device. It can be seen that the proposed model is accurate enough to capture the trend of the force time history. So the concept of the fluid inertia can be exploited in a novel device, in a novel system called a tuned fluid inertia. It's for the protection of buildings. We are talking about a fluid inertia that is attached to the ground and that is connected to a very light mass, I mean a rigid planar frame in this configuration, and it's just aimed to create a rigid diaphragm behavior. And this membrane element is connected to the isolation flow to this additional set of auxiliary isolators. So the fluid inertia is somehow tuned to the frequency of the isolated building, and it can exploit the inertial and damping properties of the fluid inertia in combination with the base isolation systems, like in this example of friction pendulum bearing. We numerically tested the performance of this system, considering a wide set of records, in particular 44 fault-field records and 56 near-fault records, of which 28 pulse-like records, which are particularly critical for base-isolated structures. And we tested the performance. We first optimized the parameters of the auxiliary isolators by a stochastic-based design procedure. In particular, we proposed an energy-based design procedure to find the best properties of inertance and damping, which are related to the radii of the helix and to the radius of the piston. I will show this concept in a minute in the next slide. If we have a look at the seismic performance, I report here the performance in terms of maximum displacement, maximum interstitial drift, and maximum absolute acceleration of the considered benchmark 6-story reinforced concrete structure, isolated with different technologies. So with classical friction pendulum system, with friction pendulum in combination with the tuned mass damper inertia, in combination with the tuned mass damper, in combination with the tuned fluid inertia. It can be seen that especially for near field records, the performance enhancement is really impressive in the proposed fluid inertia. And we focus on the time history of the response for a couple of pulse-like records, in particular the Imperial Valley and the Irpinia record, and we compare the performance in terms of last floor displacement and last floor acceleration of this building, and it can be seen that the reduction are very, very good. We reduced the displacement of the isolators of more than 50% and the absolute acceleration of more than 20%. So the question is how can we design this device in order to accomplish the desired target inertance and damping parameters? Because there is a complex geometry involving different dimensions. So we proposed the use of specific graphs, design graphs, whereby fixing some dimensions with some reasonable judgment, engineering judgment, there remain just two free parameters that are the radii of the piston and of the helix. And for this specific case, for this specific six-story structure, we came up with a device which is just 1 meter long and 70 centimeter wide, which is quite compact compared to the realistic building. So I go to the conclusion. I have focused on my presentation on the peculiar characteristic of this device, of the inertia, which is aimed to selectively modify the inertia property. This is quite different from a typical addition of a mass, because the inertia works in terms of relative acceleration, not absolute acceleration. So it can be used to improve the performance of TMD system. It can be used to improve the performance of a base isolation system. And among the two variants, the mechanical and the fluid inertia, there are some advantages in using the fluid inertia, in particular with respect to pulse-like ground motion, as I have shown in my presentation. So next step is to test this device from a small scale to real scale, to some testing in our laboratory at the University of Messina. We have a checkable test capable of performing 3D tests on isolator and dissipation devices. I have concluded my presentation. I wish to thank you all for your attention.